All right. Hello, everyone. Thank you very much to the organisers. This has been really great so far. I'm very happy to be here. So what I want to do today is talk about some concerns about the relationship between emergence and relationalism or perspectivalism in quantum mechanics. I'm going to argue that some considerations about the way relationalism seems to work in the context of quantum mechanics potentially poses some problems for the traditional way that we think about emergence in this context. So I'm going to start by explaining why we should care about this, why one might think that relational descriptions are going to be important in the context of quantum mechanics and beyond. I'll then talk about the question, if quantum states or descriptions are relativized, what are they relativized to? I'll describe how that might pose some problems for emergence and think a bit more about what that means for internal reference frame descriptions. And finally, I'll briefly speculate on the relationship between reference frames and Wigner's friend. So here is a sort of general worry about emergence in this context. There are good reasons to think that at least some quantum descriptions, perhaps all quantum descriptions, have to be relativized to something. And moreover, I'm going to present some theoretical results suggesting that we probably are only going to get the full quantum formalism in the limit as the reference becomes large, as the reference becomes a quasi-classical system like a human observer. Now, if that's right, then it seems to me that there's a problem with trying to use the quantum formalism in its usual form to describe the emergence of classical space-time and the classical world. There's a worry that by using quantum mechanics, we are implicitly presupposing some pre-existing classical reference frame. So there's some kind of circularity involved here in using the quantum formalism to try to get the classical world to emerge. So that leaves us with a question about what it might look like to try to describe the emergence of the classical world and space-time itself without sort of presupposing an external classical reference frame. So I'm going to start by explaining why we should think that quantum descriptions might sometimes be relativized or always be relativized. Within quantum mechanics, perhaps the strongest motivation comes from the Wigner's friend scenario. So we probably all know this one. We're going to put our friend Chidi in a box and have him perform a measurement on a system S in the superposition state shown here. We'll have another friend, Alice, who's standing on the outside, and she has complete coherent control over the whole contents of the box. So if we apply unitary quantum mechanics from Alice's point of view, presumably after the interaction, Chidi and S are in the entangled state shown here. And presumably Alice could, in principle, confirm that they really are in this state by performing appropriate tomographic measurements. So something strange seems to happen here. Chidi presumably saw a single outcome to his measurement, but the state assigned by Alice seems to describe him as being in some kind of mixture of both outcomes at once. Now, obviously, one way to solve that problem is just to deny the universality of unitary quantum mechanics. We could say, in fact, the wave function collapses universally for everyone when T does his measurement, so the state shown on the previous slide is not, in fact, the right one for Alice to use. But for reasons of theoretical simplicity, elegance, and so on, we've got some good reasons to think that ideally we would like to maintain the universality of unitary quantum mechanics. So here I'm going to assume that unitary quantum mechanics is always correct for all observers, meaning in this scenario that the wave function doesn't collapse for Alice except when she performs a measurement, and likewise the wave function doesn't collapse for Chidi except when he performs a measurement. What that means is that immediately after Chidi performs his measurement, the state of S, which correctly predicts the outcome of his next measurement, if he makes one, is going to be either 0 or 1, depending on the measurement outcome. And at the very same time, the state of S, which correctly predicts Alice's next measurement on S, if she makes one, is this mixed state here, which I obtained from the state on the previous slide by just tracing out Chidi. So what we see pretty clearly from this example is that if unitary quantum mechanics is always correct for all observers, it's inevitable that we're going to have some kind of relativization within quantum mechanics, in the specific sense that there are scenarios in which the state which correctly predicts one observer's next measurement is different from the state which correctly predicts another observer's next measurement. Now, that relativization doesn't have to involve any sort of radical subjectivity or anything. We have relativization of this kind within various fairly mainstream approaches. So in Everett, we have relative states relativized to branches of the wave function. So in the scenario we've just described, we get different relative states because Alice and Chidi are in different parts of the wave function. Similarly, de Broglie-Bohm has conditional wave functions relativized to different sets of de Broglie-Bohm particles. And then meanwhile, we have the more relational approaches like relational quantum mechanics, which relativize states in a more radical way and don't allow any observer-independent states at all. So what we learned from the scenario is that some kind of relativization is going to be necessary, but there's quite a lot of freedom in what exactly that might look like. Moving outside of quantum mechanics, we get other motivations for relativization that maybe will help us narrow down what kind of relativization we're dealing with. Of course, when we move to gravity, we have a variety of challenges arising from the fact that we don't necessarily have a fixed space-time background to work with anymore. So we can't describe our physical systems relative to a fixed space-time background. In particular, the standard interpretation of GR says that histories related by a diffeomorphism are physically identical. What that means is that any variables defined at individual coordinates, like the momentum of the particle at time t, are not by themselves physically real, and descriptions of things relative to space-time points are not meaningful. What is physically real then? Well, two main classes of variables, either highly non-local quantities defined over the whole of space-time, or relational quantities built out of correlations between field values. Obviously, the former isn't going to figure very much in our everyday experience, so most of the things we observe in our ordinary lives, including most properties that we ascribe to things, are going to end up being relational observables. So, for example, the momentum of the particle at time t becomes the momentum of the particle relative to the clock reading time t. So what we see is that in gravity, we have to do property ascriptions relative to other physical systems. Properties will have to be ascribed relative to a rod, a clock, or something like that. And quantum states, of course, either are properties of systems or describe or assign probabilities over properties of systems, depending on your interpretative approach. So that makes it look like, in this context, quantum states are going to have to be relativized too. Moreover, if quantum mechanics is universal, then the reference systems are also quantum. So we're going to end up having to describe quantum systems relative to other quantum systems. So this kind of consideration, I think, is an argument not just for the existence of some kind of relativization within quantum mechanics, but for the idea that probably all quantum descriptions or all quantum states must be relativized to something. It perhaps isn't going to make sense to assign quantum states in an absolute relative reference independent way. Finally, given that we have the emergence of relativization in the Wigner's-Friend scenario in just quantum mechanics, and we also have some other kind of relativization that seems important in the context of gravity, it's been suggested by various people that relational approaches to quantum mechanics are very likely to help us with attempts to unify those two theories. So Vidotto, for example, argues that the relationality in relational quantum mechanics is just the same kind of relationality that we see in the relativity theory, and that this is kind of ubiquitous in modern physics. I think some care is required here because the word relational is very broad and general, and you can kind of describe anything as being relational in some sense if you sort of squint. But nonetheless, it seems fair to say that there's some kind of trend emerging here that we should take seriously. So with that in mind, I'm going to sort of proceed from here based on the assumption that all quantum states or all quantum descriptions have to be relativized to some kind of physically meaningful reference frame, and I'm going to think about what that means for emergence. Okay, so we've seen good reason to think that quantum states should be relativized to something. That leaves us with a further question about what kinds of things quantum states and descriptions can be relativized to. So from the Wigner's-Friend scenario, we have good reason to think that they should sometimes be relativized to observers or to physical systems that play the role of observers. But can they be relativized to anything else? So I sort of see two schools of thought on this in the literature. What I'll call the anthropocentric approach says that quantum states and descriptions are relativized only to observers, where that seems to be intended to mean conscious observers or human observers or something like that. So that includes certainly the Neo-Copenhagen approaches, various pragmatist approaches, possibly cubism. The alternative then is the quantum universalist approach. This approach says that, in fact, quantum states can be relativized to any physical system whatsoever. And so that is the route taken in particular by relational quantum mechanics. Some perspectival modal interpretations also do this. And more generally, if you're familiar with the quantum reference frame formalism from Quantum Foundations, it seems to me that that formalism is in effect taking a universalist approach because it's trying to figure out how to write down quantum states relative to all sorts of arbitrary physical systems. So both of these approaches, I think, have some drawbacks. The anthropocentric approach is, of course, not very appealing for realists who generally think that observers should be describable in physical terms and shouldn't play a sort of fundamental role in the formulation of the theory. I also think the anthropocentric approach is not that good a fit for what's going on in gravity, because on the gravity side, there's no suggestion that relational observables have to be relativized to conscious observers or to humans or anything. They can be relativized to all sorts of things. So the anthropocentric approach maybe doesn't seem like the right way to go if we're concerned with this problem of unifying quantum mechanics and the gravity side. On the other hand, universalism, while it's sort of more appealing on the sort of conceptual grounds from my point of view, it does seem to encounter some quite significant technical problems. So in particular, if we're going to ascribe a quantum state relative to some system, we would presumably like that to have some content, some kind of meaning. If the system is a human observer, we can give that meaning in terms of the measurements that the observer can do. If the system is not a human observer, presumably it's going to be something to do with the relations between the systems or the types of interactions they can undergo. But for really small physical systems, it doesn't look like there's going to be enough resources to meaningfully define a contentful quantum state. And so it starts to seem unclear what those descriptions could actually mean. So this point is particularly emphasized by Bruckner in this paper, Qubits Are Not Observers. He's writing here about relational quantum mechanics, but I think the concern he's raising here is relevant quite generally for various universalist approaches to relationalism. So in relational quantum mechanics, the way in which we give sort of content to the relational quantum states is to say that when two systems interact, an observation is made, so a variable of one system becomes definite relative to the other system, and the quantum state is used to give the probabilities for various variables to be chosen. So that's all fine, but before we can make sense of this, we have to decide which basis does this interaction take place in. That is, which basis are we using to choose one variable probabilistically according to the prescriptions of the quantum state. So there's an obvious way that you might go about answering this, and it would involve appealing to the Schmidt basis. The thought here is that when two quantum systems interact and become entangled, there's always a Schmidt basis in which the resulting state looks particularly simple. So in particular, the Schmidt basis, as you see here, has no cross terms, just has the 0, 0 term and the 1 term, 1 term. So it sort of makes sense to say that when we have this kind of interaction between two systems and we want to define an observation or a measurement, we should say that's going to be happening in the Schmidt basis. That's because you can sort of see a natural interpretation of the Schmidt basis where the first term here corresponds to the system is in state 0 and the observer store the result 0. And then the second term corresponds to the system is in state 1 and the observer saw the result 1. Whereas in the non-Schmidt basis, it's kind of hard to understand how you should interpret the 0, 1 and 1, 0 terms. So great, if your Schmidt basis is unique, you're kind of done. You can use the Schmidt basis to decide which basis this variable becomes definite in. But the Schmidt basis is not going to be unique if there is any degeneracy. So if we're dealing with two very large systems interacting, the probability that more than one or two coefficients is degenerate is going to be very, very small. And so in that case, we can sort of see that the Schmidt basis is going to be sort of at least approximately unique. Most of the possibilities will be ruled out. We'll have sort of perhaps a small number or a small range of possibilities for the sort of ways in which that interaction could take place. Or of course, in that scenario, we can just appeal to the basis that's favored by decoherence. But what if we're dealing with a pair of qubits interacting and becoming maximally entangled? Well, in that case, the Schmidt basis is not even approximately unique. Given any Schmidt basis, applying a joint unitary transformation to the two qubits will generate another Schmidt basis. So what that means is effectively any basis of interaction will correspond to a Schmidt basis. There's no structure here at all. There's no possible way to sort of narrow down a basis in which this observation would take place. And that, I think, makes sense. If you just look at an entangled state of two qubits, it's kind of obvious that there's nothing there that could possibly sort of single out a particular basis of interaction in which that observation could take place. So this is just one aspect of the sort of problem of observation, but what you can sort of see here is that for a pair of qubits, it seems very hard to understand how you could give sort of meaningful physical content to the ascription of a quantum state to one of them relative to the other one. There just doesn't seem to be enough structure there to understand what that would actually mean. So for that reason, I think there's potentially an appealing third route when we start to think about how to do relativization of quantum states. I'll refer to that as the emergence route. And the idea here is that we can always give a description of one physical system relative to another physical system, but this is going to approximate the full quantum formalism only in the limit as at least one of the systems becomes sufficiently large. So that means that the quantum formalism is going to be the right way to describe, for example, the physics of microscopic particles relative to a conscious human observer, but it is not necessarily going to be the right way to characterize the state of one microscopic particle relative to another microscopic particle. The thought here is that the state of a system S1 relative to another system S2 should reflect the actual physical resources available to S2 so that that state can have some sort of physical meaning. In particular, we'll see that's going to help solve the problem posed by Bruckner, because a qubit, of course, doesn't have many physical resources, so the state relative to a qubit should be quite simple. In fact, I'm going to argue that the state relative to a qubit should be just a probability distribution over the outcomes of one possible measurement, and so we can see that there's not going to be a preferred basis problem there because we don't have alternative possible bases. There's in fact only one possible measurement. So the emergence approach, I think, inherits some of the virtues of the other two approaches and hopefully has fewer problems. In particular, the emergence approach shares with anthropocentrism the idea that at least some features of the quantum formalism probably reflect special features of human observers rather than necessarily intrinsic features of the systems we are trying to describe. In the emergence case, the thought is that the special feature that's relevant is our size. We are large systems, so we are perceiving things relativized to macroscopic systems. We shouldn't necessarily assume that exactly the same physics will be relevant when we're looking at things relativized to significantly smaller systems. On the other hand, the emergence approach also shares with universalism the idea that human observers shouldn't be privileged in the formulation of the theory. So the thought is that we should just arrive at human macroscopic observers as the limit of some kind of emergence process rather than them being treated in a special way in the formulation of the theory. Okay, so what can we do if we are interested in trying to write down the state of one microscopic system relative to another microscopic system? Now, there are already several research programs within Quantum Foundations concerned with this problem of writing down the states of systems relative to each other and transforming between them. But I think neither of the sort of mainstream approaches in this regime really answers the question that I'm trying to pose here. So let's just have a look at what those do. There are sort of two main routes that people take to study quantum reference frames. The structural approach is all about trying to break the redundancy that arises when we try to describe the quantum state of a system without external reference frames. And so the way that works is we take our system S, we choose a subsystem of that system S, and then we use symmetry transformations to write down the state of the rest of S relative to the subsystem, thus fixing a unique representation for the state. So in some sense here we have written down a state of the rest of S relative to the subsystem. But this is essentially a coordinate transformation, right? All we're doing is choosing a representation of the state as it was described relative to the external observer. We're not making any attempt to take into account the resources available to the subsystem that plays the role of the reference. We're not really trying to write down a realistic or operationally meaningful perspective for that system. This is kind of acknowledged by people working on this formalism. Here, for example, we have Krum et al. Noting that one could ask whether observers who are part of the theory may have operational access to that reference frame, but that's an additional and secondary question that's not sort of the central focus here. What they're trying to do is write down a coordinate transformation, not to write down an operational description of a perspective. The alternative is what's known as the quantum information approach. And so the quantum information approach is primarily applied in scenarios where an observer does not have access to a reference frame for some system, and the goal is to understand what operational tasks the observer can complete. So, for example, what information they could extract from that system. Now, the QI approach seems kind of more what we're looking for here. It is operational in character. It is thinking about resources and sort of physically meaningful operations. But by construction, the observer here is always a classical observer. The observer is an observer like us. The QI approach doesn't really seem to be trying to take the extra step of going into the system and describing it from the point of view of a system internal to that larger system. So in particular, it doesn't really tell us how you might describe a quantum system relative to another small quantum system. It's all done from this external classical perspective. So while these approaches are both useful, and I'm going to use some tools from both of them, I don't think either of them quite answers the question that I'm trying to pose here. Okay, so with that in mind, what does it look like to write down the internal state of one system relative to another one if we are really trying to make that reflect something that is sort of physically meaningful about the relationship between them? So there are various choices you might make here in trying to understand what that should look like. I'm going to just use a couple of principles which seem sensible to me to kind of narrow down what that description should be. The first is intrinsicality. So that just suggests that the internal state of some system S relative to R should contain only information about the relationship between R and S by themselves. That is to say, it should be definable without reference to any external reference frame. The other is resource relativity. So the internal state of S relative to R should scale with the resources available to R. That is, I'll take that to mean that the amount of information encoded in the internal state of S relative to R can't be greater than the information that could be extracted about the relation between S and R by some external classical observer. So the thought here is just, I'm going to assume that there isn't sort of extra information hidden within the reference frame that you couldn't get from the outside. Whatever information is there in that internal reference frame is also accessible from the outside by an appropriate interaction. So there's a tool that is used in the reference frame approaches in general that's going to be useful for us here. Ooh. Just temperamental. Okay. Okay, here we go. So yes, there's a technique that's going to be very useful to implement these two principles known as group averaging. So basically the thought is that when we describe our system and reference relative to some external reference frame, that contains redundant information about the relationship to the external reference frame, but we can get rid of that information by just averaging over states in such a way that all states which are related by a symmetry transformation are mapped to a single state. So that just removes the sort of extra information about the relation to that external reference frame and leaves us only with information about the relation between the system and the reference. There are two different versions of this. There's an incoherent version and a coherent version. I'm going to use the incoherent version here because it is usually regarded as being the right approach in the scenario of an external observer who doesn't have a reference frame, which is the sort of scenario we're trying to access here. So the incoherent group averaging just looks like this. We're averaging over various members of this group to give us a state that is invariant under those transformations. Great. So using the technique of group averaging, we can put the two principles I gave you on the previous slide into a slightly more formal language. So here we're going to say, suppose we have some property of the system S, let P be the probability distribution over the possible values of P, which will be predicted by the internal state of S relative to R. Then I'm just going to say that this probability distribution should be isomorphic to the distribution we could get from performing some measurement on the relevant group average state. So we're imagining an external observer who doesn't have a reference frame looking from the outside and measuring something about the relation between them. And so the thought is the distribution from the internal point of view should map on to what you see from the outside when you try to measure some kind of relational quantity. Yes. Yes, sorry, that's a typo. Yeah. Great. So let's use that description to try to write down some things about what we might see for the internal state in some particular cases. So I'm going to consider the case where our system is a spin-half system and our reference is also a spin system of spin G. The symmetry group here is going to be the spatial rotations. So we'll be averaging over spatial rotations to generate a state which just tells us about the sort of relative orientation of these two spins. So we'll start from a case where, relative to some sort of hypothetical external reference frame, S is in the state shown here, and R is in some eigenstate of maximal spin along the zero axis. So the principle I've just suggested says that the probability distribution over the value of spin of S relative to R must be isomorphic to the result that you can get from performing some measurement on the appropriate group average state of the two systems together. And to get something non-trivial here, we have to choose measurements which commute with the rotation group. Sort of the only meaningful option here is going to be the total angular momentum measurement, and that does make sense here because total angular momentum can be thought of as measuring whether these two spins are parallel or anti-parallel. So the result of that measurement tells us either S is up relative to R or S is down relative to R. So that seems to be the right kind of measurement. So we can calculate what the probabilities for the result of that measurement is. They're found to be parallel with the probability shown here and anti-parallel with the probability shown here. So as you see, for small values of G, the probabilities diverge from alpha squared and beta squared, which is what you might expect if you just looked at the state of the system S relative to the external reference frame. In particular, the parallel result becomes slightly more likely, the anti-parallel result becomes slightly less likely. So we are sort of deviating from the quantum description relative to the external frame. Okay, so what then is the state of S relative to R? So you might at first think, I'll just change the coefficients in the state to reflect these different probabilities, giving me my state relative to R. But of course, that's perhaps not sufficiently general. We should take into account the possibility that there could be a relative phase or that it could be a mixed state. So the most general form for that state is going to be the density matrix shown here, where I've put those two probabilities on the central axis. Of course, we need three parameters in total to pin down a density matrix for a qubit. So we have the other parameters, AX and AY. And the problem we now encounter is that there is no other measurement we can do here to get any non-trivial probabilities. The total angular momentum is the only non-trivial measurement that's available, looking at just that system and the relations between the two spins. So there's no way we can possibly fix AX and AY here. So in effect, we can't really get a quantum state at all for the state of S relative to R. What we get is, as I promised earlier, just a classical probability distribution over the outcomes of one measurement, because there is only one meaningful measurement you can really make here. The only meaningful question you can ask is, are they parallel or anti-parallel? There's no other options really in this case of two spins. So this, as I sort of suggested, is going to help us resolve Bruckner's problem. We don't have multiple bases to choose from. There's only one option here in this particular case. Now, what do you do if you do want to obtain a quantum state? Well, the first thing you're going to have to do is add more spins to your reference system so you can define some more measurements. So, for example, suppose we add a couple more spins of spin G, and let's arrange them to be orthogonal to each other so we get a sort of orthogonal reference system. So in that case, we have three possible measurements that we can do. We can check if S is parallel to every one of the three spins, and we can use that to define the parameters in the density matrix. So, of course, you can't do all three of those measurements in any one case. You'll have to do separate preparations and test them. But that's just the same as usual in quantum tomography. You can't do all the tomographic measurements on a single preparation. You have to do it multiple times. So doing a similar calculation to the one I did before, where you can fix those parameters, and then we get a density matrix with the block vector shown here. And what you might observe about this block vector is that it's not a valid block vector. Its magnitude is greater than 1. So actually, in this case, we still don't get a valid quantum state. We do get a full density matrix where we have fixed all the parameters, but it's not actually a valid density matrix. Why is that? Well, you can kind of get an intuition for it by thinking about the result of what happens here when we think about the quantum uncertainty relations. So in particular, for an ordinary quantum state, if our spin is in an eigenstate of spin along the x-axis, for example, then it should be maximally uncertain along the y and the z-axes. So you should get 50-50 probability for the parallel and anti-parallel results along the y and the z-axes. But as we saw earlier, in this kind of case, we always end up being slightly more likely to be parallel than anti-parallel. The spins kind of get attracted towards each other. So what that means is that the state that we get, that we define looking at these measurements relative to this reference system, ends up slightly violating the quantum uncertainty relations, because if our spin is maximally certain along the x-axis, it's not maximally uncertain along the other two axes. So it's not quite a valid quantum state because it doesn't obey those requirements. But what you can see is that as G goes to infinity, the magnitude of the block vector does approach 1. So as the three reference systems become large, we do get a valid quantum state. We get back the original quantum formalism. So what we kind of see here is the sort of the behavior that I was kind of gesturing at. As our reference system becomes essentially classical, we end up with the full quantum formalism relative to that reference system. But if our reference system is very small, if it's similar to the size of the system we're describing, we're not going to get an ordinary quantum description. We can also say something more general just by looking at features of the group average state that we are using to define the internal state. In particular, given the condition I set out earlier, the information content of the internal state of S relative to R should be equal to the mutual information between R and S in some group average state, anyone. And so following the standard quantum convention, we can say that the maximum information content of a state in the internal state space is going to be the log of the dimension of the internal state space. So we can use this to say something about what the size of the internal state space is. So the group average state is always going to be block diagonal, with each block corresponding to one of the invariant subspaces, and the von Neumann entropy of that matrix is just the sum of the von Neumann entropies of the blocks. So if there are no non-trivial invariant subspaces, the mutual information is always going to be 0. If there are various different invariant subspaces, the structure can become quite complex. But if we just look at the simple case where the two systems individually don't have non-trivial invariant subspaces, but together they have one non-trivial invariant subspace of dimension n SR, then we can calculate the mutual information, and we can see it's just going to be equal to log the dimension of that invariant subspace. So what we kind of see here is that the dimension of the internal state space of S relative to R, if we sort of use the prescription I've suggested, is going to be upper bounded by the dimension of the invariant subspace of S times R. In particular, there is no invariant subspace for 1, 2, or 3 qubits, but there is a subspace of dimension 2 for 4 qubits. That kind of matches what we previously saw. We saw that we need a reference made up of 3 independent qubits to get a full quantum state space for 1 qubit. So we need 4 qubits in total to get a single qubit internal state space. For less than 4, we can get classical probability distributions, but we can't get a proper quantum Hilbert space. More generally, for an array of n qubits, if x is the number of qubits we can encode in the invariant subspace, then the ratio of x to n is going to behave as 1 minus 3 over 2 log n over n in the limit of large n. So that obviously goes to 1 as n becomes large. The point here is that for a large enough number of qubits, the internal state space fits the whole state as it would have been defined relative to an external reference frame. So in the limit, as the reference becomes large, we get back our original quantum description. So again, this kind of supports the emergence approach I was talking about. It does seem true to say that we get the full quantum description only in the appropriate limit. Okay, so the good news is that this can straightforwardly solve Bruckner's problem. So for those who like RQM in particular, this is good news. What we've seen here is that the internal state of one qubit relative to another qubit is just a classical probability distribution over 2 outcomes. Only one possible measurement here. There couldn't possibly be a preferred basis problem because there's only one basis. But more generally, I think this potentially poses problems for when we talk about emergence involving quantum mechanics in general, both the emergence of the classical world from the quantum regime and also plausibly the emergence of space-time from some sort of quantum substratum. The worry here is that if it's true that quantum states within the standard formalism only really make sense when relativized to some macroscopic reference system, that's going to suggest that probably quantum states of spacetime also have to be relativized to some macroscopic system. And that the very idea of a macroscopic system, I would say, necessarily presupposes some background spacetime in which that system lives. Seems hard to understand what would it even mean to call something macroscopic without appealing to a background spacetime. So I think there's a worry here that there's some kind of sort of hidden circularity when we're trying to get space-time to emerge from a quantum description, because the whole thing seems to need to presuppose a space-time in which the reference system lives, but before we can start using that quantum formalism to describe the quantum states of space-time. Now, obviously, this will vary framework by framework. You might, for example, start with some substratum and then go directly from that substratum to appropriate relational descriptions, in which case maybe the substratum itself doesn't need to be relativized to a macroscopic system. But I think the points I've just made do give us some reason to be careful about the assumptions we are making about the nature of that substratum. In particular, if the state of one qubit relative to another qubit is not quantum in the ordinary sense, the intrinsic description of 2 qubits without reference to an external reference frame is also not going to be quantum in the ordinary sense. And so you might think the intrinsic description of things much smaller than qubits, such as atoms of space-time or whatever it might be, might not be quantum in the ordinary sense either. So we should perhaps be careful about the assumption that the quantum formalism is going to be the right way to think about these questions. In particular, we should keep in mind, I think, the possibility that space-time itself must emerge relative to reference frames and may not be well defined in the absence of an appropriate and probably macroscopic reference frame. So this can be illustrated by considering a Wigner's friend scenario where the variable measured is spatiotemporal. So I'll look now at a case where the variable is spin. Spin is, of course, associated with direction in space-time in the rotation group. So the emergence of space-time is going to be relevant to the description of this scenario. So I described already the standard Wigner's friend scenario. I now want to move to a slightly more complex example, which is the Bong et al. Wigner's friend local friendliness paradox. So here we are basically going to perform two different Wigner's-Friend scenario experiments linked together by entanglement between the systems that are being measured. So we'll have our friends Ellis and Chidi performing measurements on two halves of an entangled 2-qubit state. Then Bob is going to keep Ellis's laboratory in a coherent state and perform a measurement on it. And meanwhile, another observer, Divya, is going to keep Chidi's laboratory in a coherent state and perform a measurement on it. So we end up, therefore, with 4 possible measurement outcomes, A, B, C, and D. So the important point to note here is that although the usual prescription is that Bob should perform a certain super measurement on Alice's laboratory while it's in a coherent state, in principle, Bob also has the option of just giving up on the experiment and going into Alice's laboratory and asking her about her outcome. So in that case, presumably, Bob would just find out the value of A. He would find out what outcome Alice has seen. What that means is that Bob, on any given run of the experiment, can choose to find out either A or B, and meanwhile Divya can choose to find out either C or D, and then at the end Bob and Divya will talk to each other and both find out what the same variables that they each had. So the end result is that at the end of the experiment, Bob can find out the value of one pair of variables from the set here. So he can either find out BD, BC, AD, or AC. Moreover, if we're assuming locality and we're assuming no retrocausality and no superdeterminism, presumably then the probability distribution over the results of these 4 measurements can't depend on whether Bob subsequently makes a choice to find out B or instead to find out A, and therefore it seems natural to say the probability distribution over these 4 variables needs to obey the predictions of quantum mechanics for any one of these pairs. So it should match what quantum mechanics predicts pairwise, if not necessarily for all 4 things. So what that means is that on any given run, it seems like we ought to be able to get the predictions of quantum mechanics to be matched for all 4 of these pairs. And then the theorem that's proved here is that this is not possible. Bong et al. Show that there is no possible distribution which always reproduces all the pairwise predictions for all 4 of these pairs. So something has gone wrong here. At least one of the assumptions that's gone into this result needs to be denied. So obviously one easy way to resolve the paradox is just to allow non-locality or retrocausality. That will solve the problem. But in the sort of relational point of view, perhaps we want to give a more specifically relational solution, which takes advantage of some of these ideas about reference frames and relative quantum states. So there's been quite a lot of discussion about that kind of possibility with respect to an assumption that has been called absoluteness of observed events. So the thought here is that when we sort of set out this probability distribution over these 4 variables, we are assuming that there is some fact of the matter about what Alice observed and what Bob observed, and about the relation between those 2 things. If we deny absoluteness of observed events, if we just say there's actually no fact of the matter about the relation between Alice's observation and Bob's observation, then it seems like we can just deny that there exists any probability distribution over all 4 variables together, and so we can resolve the problem. However, I think this is not a very appealing route. The reason this is not an appealing route is because it leads to really severe epistemic problems. If there's no fact of the matter about the relation between Alice's observation and Bob's observation, it seems impossible to say that when Bob talks to Alice, he finds out what she really saw. And so this route seems to be in danger of just undermining all of the assumptions we typically make in science about our ability to communicate with other scientists, learn about their results, critique each other's results, and so on. So for sort of methodological reasons, this to me looks like a just not an acceptable solution to the problem. I want, therefore, to propose an alternative approach, which I think has something of the same spirit, which sort of maintains the idea that there's something relational that's important going on here, but which doesn't force us to kind of abandon all possibility of communication between observers. So the alternative is to take seriously the idea that the spin measurement needs to be relative to a reference frame, and to say, well, perhaps there is no fact of the matter about the orientation of Alice's axis relative to Bob's, unless and until they interact and share information about that. But there is always a fact of the matter about what Alice has seen within her internal laboratory. That's a well-defined fact. It's a fact that Bob can find out if he talks to her, and there is a sort of well-defined relationship between what Alice has seen in her laboratory and what Bob has seen. So specifically, in any given run, Alice has either seen that the spin is parallel with her axis that she's using to define the x direction, or she sees that it's anti-parallel to her axis that she's using to define the x direction. And that fact can be well defined, even if there is no well-defined relationship between the direction of Alice's x-axis and the direction of Bob's x-axis. So that gives us a way to sort of think a little bit differently about what's going on in the Bong et al. Paradox. So recall that we had our probability distribution over 4 variables, A, B, C, and D. Once we start thinking about the role of reference frames here, we can sort of see that there's a bit of an ambiguity in the definition of this variable A that's supposed to describe Alice's measurement outcome, because A could be the variable defined by Alice's own internal observation. So either Alice saw down relative to her axis or Alice saw up relative to her axis. That's an internal fact about Alice's configuration. Or A could be the variable AE, which is defined within Bob's reference frame, which kind of combines the facts about what Alice saw internal to her reference frame with facts about what direction her axis is found to point in relative to Bob's axis. So for example, if Alice sees up relative to her reference frame, and then subsequently Bob finds that her x-axis is pointing in the same direction as his x-axis, he will conclude that the result was up relative to his axis. Whereas if Alice sees up relative to her x-axis, but subsequently Bob finds that her axis points down relative to his x-axis, the conclusion for Bob is that the spin was down relative to his x-axis. So finally, what I'm going to assume here is that we don't by default have a relationship between those two axes. So in particular, I'll suppose that Alice's axis comes to have a well-defined orientation relative to Bob's axis only in the case where Bob actually checks. So specifically, if he measures to find the variable B, he doesn't check, he doesn't talk to Alice. In that case, there's no well-defined relative orientation at any point. But if he talks to Alice instead of measuring to find B, then during that interaction, those axes become aligned, and so after that there is a well-defined fact of the matter about the relationship between them. Great. So when we talk about this idea of absoluteness of observed events, I think the natural way to interpret that requirement is to say that it is asking that there should be a well-defined probability distribution across the variables AI, B, C, I, and D. So Alice's internal variable rather than the external variable relative to Bob. That's because kind of the whole justification for this principle was supposed to be the idea that what we observe is it must be real, it must be absolute. And so what Alice observes here corresponds to AI and not to AE. So that's why that's the central thing we should insist on. So in particular, when we're thinking about these kind of epistemic concerns about the ability to have well-defined observations and communicate them, that well-defined distribution across AI, B, C, I, D seems to be what is relevant to those sort of epistemic concerns. So that I think is what we really need to insist on. But the probability distribution over AI, B, C, I, D can't be compared to any quantum predictions because quantum mechanics only makes predictions for spins measured relative to some common space-time reference frame. And by construction, there is no common reference frame here. AI is just an internal statement about Alice's laboratory. We don't know what it means relative to Bob's axis. On the other hand, AE, B, C, E, and D can be compared to the predictions of QM because all of those variables are now defined relative to the common reference frame of Bob and Divya. But there is no well-defined probability distribution across these 4 variables because by construction, AE exists only on the runs when Bob does not obtain the value B, and so we don't ever have values for B and AE on the same run. So in this case, no quantum predictions are going to be violated, but nonetheless, we get to keep absoluteness of observed events in the sense of a well-defined distribution across AI, B, C, I, and D. There will always be a well-defined fact of the matter about what Alice saw. If Bob asks her, he will find out what she saw. It's just that in the case where they don't interact, there's not necessarily a well-defined fact about what Alice's observation corresponds to within Bob's reference frame. So why should we think that's a sort of reasonable way to describe this experiment? I think a helpful way to understand that is to think about the role of symmetry groups in this description. So of course, a theory is said to have a symmetry if there's a class of transformations T which leave its equations of motions and solutions unchanged. And it seems natural to say that these transformations don't produce any physically real change. So if we now imagine applying a transformation in that group to a proper subsystem of the system, that is not going to change anything about the internal state of that subsystem, but the transformation may still be detectable when we compare the subsystem to its environment. So that's true for the rotation group, for example. If we imagine applying a rotation to Alice's whole laboratory, that's not going to change anything about the internal configuration of Alice's laboratory. It presumably won't change anything about Alice's experiences within that laboratory, but it will change the relation between Alice's laboratory and Bob's laboratory if we're sort of leaving Bob's laboratory unrotated. So in particular, a variable of the subsystem which is changed by a transformation like that is not meaningful when we consider the subsystem in isolation, but can still be meaningful when compared to an external reference frame. So with that in mind, we can sort of see a different possible way of writing the quantum description of what happens in this experiment. So assuming here that we have a rotation symmetry, rotations don't change the internal state of Alice in her laboratory, then it seems natural to say that the variable AI, Alice has seen the spin parallel to her axis or anti-parallel to her axis, lives in the invariant subspace with respect to the rotation group. Rotating the whole lab won't change the facts about whether the spin and referent and axis are parallel or anti-parallel. But rotations of Alice's laboratory are meaningful with respect to Bob's laboratory. So we can imagine a superposition like the one shown here. So here, PA and P'(A) represent states of Alice which are internally the same, but which are different from Bob's point of view. So I'll say these are states where she has observed the particle to be parallel to her own axis, but they have different total orientation relative to Bob. So what we see is we still get a superposition here, and yet from Alice's point of view, both sides of the superposition are the same. These terms are different only relative to Bob and not from Alice's internal point of view. So here this is the standard description of the Wigner's-Friend scenario, where we have an up state and a down state, which is transformed to one term where Alice sees the result up and another one where Alice sees the result down. An alternative proposal making use of these kinds of symmetry transformations would involve suggesting that after the Wigner's-Friend experiment, in the case where Alice observed the particle to be up relative to her axis, the overall state relative to Bob should be represented as follows. So here we have a state in which there is a well-defined fact about what Alice saw, and if Bob measures the invariant subspace, he will find that out. He will find out that she saw parallel relative to her axis. But nonetheless, if he performs quantum experiments on the orientation variable, he will still see quantum interference and reproduce the usual quantum predictions because these two terms are different relative to him. They have different orientation from his point of view. So what we get here is a scenario where we still get to maintain the universality of quantum mechanics in the sense that Bob still gets a superposition state and can detect that superposition state by tomographic measurements. But nonetheless, we do also get to say there was the whole time a well-defined fact about what Alice saw internal to her laboratory. Sorry, yes. Yes, but in order to be able to do this experiment, Bob has to keep Alice in a coherent state, which means he needs to isolate her from the environment. So what I want to conjecture here is that process of isolating her in some way removes the shared reference frame.
It's not spin measurement, but just like a cubic measurement, like energy level system, like a level system.
Yeah, so basically to make this work for other types of spins, other types of variables, you would have to identify a relevant symmetry transformation there as well. So I thought mostly about this in the case of spin. I would conjecture that there will be relevant symmetries for the other cases as well, but we'd have to think about that case by case. Mm-hmm. Great. So if we buy that as a resolution to the paradox, which you may or may not do, it seems that then the paradox arises precisely from assuming that there's a fixed shared space-time background by default. Whereas once we note that each reference frame has its own space-time and that there is not by default a shared meaning of orientation, the paradox can be resolved. So we can think of this plausibly as a manifestation of the idea that space-time is defined relative to reference frames, that something about the process of isolating Alice in order to do this experiment takes away the shared reference frame and leaves us without facts about relative orientation in such a way that we are able to resolve the paradox by trading on the difference between variables that are internal to Alice's laboratory versus the sort of relational observables that are used to define relative orientation. Great. So to conclude, there are definitely good reasons to think that at least some and possibly all quantum descriptions are necessarily relativized to something. And this is going to be important to remember when we think about the emergence of the classical world and classical spacetime. I think we need to think much more carefully about what kinds of descriptions are actually meaningful prior to the emergence of classical reference frames. I worry that a lot of what we're doing in these kinds of approaches to the emergence of spacetime, in some sense, presupposes the existence of an external classical reference frame relative to which all these states of spacetime can be defined. And that perhaps doesn't seem like the right way to think about things if we're really interested in describing a meaningful process of emergence. And finally, we should be quite careful about the attribution of properties to systems in the absence of an appropriate reference frame. We should be careful about when we assume that there is a shared reference frame and the circumstances in which that shared reference frame might no longer be relevant. And potentially there's reasons to think that way of thinking about things might help resolve some ongoing paradoxes within quantum foundations. So that's all from me. Thank you very much for listening, and I look forward to questions later.